ground fault current of 30 amps was measured at the main switchboard. When the 2500 amp MCB was opened, the current dropped to between 1.5 and 2 amps. The high ground fault current suggests a fault within the 2500 amp MCB section of the switchboard. Opening the MCB isolates the fault path, leading to the current drop. Possible causes include insulation breakdown in the 2500 amp MCB circuit, damaged wiring or equipment in the 2500 amp MCB section, and loose or corroded connections. Recommended actions involve several steps. Firstly, isolate the 2500 amp MCB section by keeping the MCB open to prevent further damage. Secondly, carefully inspect the 2500 amp MCB. Look for any signs of physical damage such as burns, discoloration, or loose connections. Thirdly, check the wiring and equipment connected to the 2500 amp MCB section. Inspect cables, terminals, and equipment for signs of damage or loose connections. Fourthly, perform insulation resistance testing. Use a megger, also known as an insulation resistance tester, to assess the integrity of the insulation within the 2500 amp MCB circuit. Fifthly, locate the fault and repair it. Once identified, isolate the affected component and proceed with the necessary repairs. This could involve replacing damaged wires, equipment, or the MCB itself. Sixthly, after the fault is resolved, reset the ground fault interrupter or GFI trip settings to their appropriate levels. It is imperative that all electrical work be carried out by qualified personnel. Always wear appropriate personal protective equipment or PPE when working with electrical equipment. Strictly adhere to all applicable safety regulations and procedures. The 30 amp reading to ground at the main switchboard warrants immediate attention. The fact that the amperage drops significantly when the 2500 amp MCB is opened is a critical diagnostic clue. Begin by visually inspecting the 2500 amp MCB and its associated wiring. Look for any obvious signs of damage such as melted insulation, burn marks, or loose connections. Pay close attention to the points where wires connect to the MCB and to any other equipment in that section of the switchboard. After the visual inspection, use a megometer or megger to test the insulation resistance of the conductors in the 2500 amp MCB circuit. This test will help to identify any insulation breakdown that may be causing the ground fault. Disconnect the conductors from the MCB and any other equipment in the circuit before performing the test. Apply the megger's test voltage between each conductor and ground. Record the insulation resistance readings for each conductor. Low insulation resistance readings indicate a potential insulation fault. Compare the readings to the manufacturer's specifications for the conductors. If the insulation resistance test reveals a fault, the next step is to isolate the faulty component. This can be done by disconnecting sections of the circuit and retesting the insulation resistance. Continue disconnecting sections until the fault disappears. The last section disconnected is the one containing the fault. Once the faulty component is identified, it must be repaired or replaced. If the fault is in a conductor, the damaged section must be replaced with new wire of the same gauge and type. If the fault is in a piece of equipment, the equipment must be repaired or replaced. After the repairs are completed, retest the insulation resistance of the circuit to ensure that the fault has been corrected. Also, verify the proper operation of the 2500 amp MCB. Ground fault protection systems are designed to detect and interrupt ground faults, which are unintentional electrical connections between a live conductor and ground. These faults can be dangerous and can cause electrical shock, fire, and equipment damage. Ground fault protection systems typically consist of a ground fault sensor, a ground fault relay, and a circuit breaker. The ground fault sensor monitors the current flowing in the circuit. If a ground fault occurs, the sensor will detect an imbalance in the current. The ground fault relay will then trip the circuit breaker, which will interrupt the flow of electricity to the circuit. There are two main types of ground fault protection systems. Firstly, ground fault circuit interrupters, or GFCIs, and secondly, ground fault equipment protection, or GFEP. GFCIs are designed to protect people from electrical shock. They are typically installed in outlets in bathrooms, kitchens, and other areas where there is a risk of water exposure. GFEP is designed to protect equipment from damage caused by ground faults. It is typically installed on circuits that supply power to motors, transformers, and other sensitive equipment. The National Electrical Code, or NEC, provides requirements for ground fault protection systems. NEC Section 230.95 requires ground fault protection for service disconnects rated 1000 amps or more. NEC Section 215.10 requires ground fault protection for feeders that supply power to equipment that is likely to cause a fire or explosion. The sensitivity of a ground fault protection system is the amount of current that must flow to ground before the system will trip. The sensitivity is typically expressed in milliamperes or mA. GFCIs typically have a sensitivity of 5 mA. GFET systems typically have a sensitivity of 30 mA. The time delay of a ground fault protection system is the amount of time that it takes for the system to trip after a ground fault occurs. The time delay is typically expressed in milliseconds or ms. GFCIs typically have a time delay of 25 ms. GFET systems typically have a time delay of 300 ms. When selecting a ground fault protection system, it is important to consider the following factors. Firstly, the type of equipment being protected. Secondly, the risk of electrical shock. Thirdly, the risk of fire or explosion. Fourthly, the sensitivity required. And fifthly, the time delay required. Ground fault protection systems should be tested regularly to ensure that they are working properly. GFCIs can be tested using a GFCI tester. GFEP systems can be tested using a ground fault simulator. The initial reading of 30 amps to ground is substantial and clearly indicates a ground fault. The subsequent drop to 1.5 to 2 amps when the 2500 amp MCB is opened is a very strong indicator that the ground fault lies within the circuit protected by that MCB. An MCB, or miniature circuit breaker, is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by excess current from an overload or short circuit. Its basic function is to interrupt current flow after a fault is detected. Unlike a fuse, which operates once and then has to be replaced, an MCB can be reset, either manually or automatically, to resume normal operation. MCB are commonly used in place of fuses in most modern low-voltage electrical installations. The current rating of a circuit breaker is the maximum amount of current that the breaker can carry without tripping. It is typically expressed in amps. The interrupting rating of a circuit breaker is the maximum amount of current that the breaker can safely interrupt. It is typically expressed in thousands of amps, or kA. The trip curve of a circuit breaker is a graph that shows the relationship between the current flowing through the breaker and the time it takes for the breaker to trip. Circuit breakers are available in a variety of types, including firstly, thermal circuit breakers, secondly, magnetic circuit breakers, and thirdly, electronic circuit breakers. Thermal circuit breakers use a bimetallic strip to detect overcurrents. When the current flowing through the strip exceeds the breaker's rating, the strip heats up and bends, causing the breaker to trip. Magnetic circuit breakers use an electromagnet to detect overcurrent. When the current flowing through the electromagnet exceeds the breaker's rating, the electromagnet trips the breaker. Electronic circuit breakers use electronic components to detect overcurrents. These breakers are typically more accurate and faster than thermal or magnetic circuit breakers. When selecting a circuit breaker, it is important to consider the following factors. Firstly, the voltage rating of the circuit. Secondly, the current rating of the circuit. Thirdly, the interrupting rating required. Fourthly, the trip curve required. And fifthly, the type of circuit breaker required. Circuit breakers should be installed in accordance with the National Electrical Code, or NEC. Circuit breakers should be tested regularly to ensure that they are working properly. A megometer, also known as a megger, is an instrument for measuring high resistance values. It is primarily used for measuring the insulation resistance of electrical equipment, such as cables, motors, and transformers. The megger applies a high direct current, or DC voltage, to the insulation and measures the resulting current flow. The resistance is then calculated using Ohm's law. Megas are available in a variety of voltage ranges, typically from 500 volts to 15 kilovolts. The voltage range should be selected based on the voltage rating of the equipment being tested. When using a mega, it is important to follow the manufacturer's instructions carefully. The equipment being tested should be de-energized and disconnected from all power sources. The test lead should be connected to the equipment and to the mega. The test voltage should be applied for a specific period of time, typically 1 minute. The insulation resistance reading should be recorded. The insulation resistance reading should be compared to the manufacturer's specifications for the equipment. Low insulation resistance readings indicate a potential insulation fault. The NEC, or National Electrical Code, is a set of standards for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA. The NEC is updated every 3 years. The NEC covers a wide range of topics, including firstly, wiring methods, secondly, overcurrent protection, thirdly, grounding, fourthly, equipment installation, and fifthly, special occupancies. The NEC is not a law, but it is adopted by many state and local jurisdictions. When installing electrical wiring and equipment, it is important to follow the requirements of the NEC. Failure to comply with the NEC can result in electrical shock, fire, and equipment damage. Article 250 covers grounding and bonding. Article 300 covers wiring methods. Article 310 covers conductors for general wiring. Article 400 covers flexible cords and cables. Article 430 covers motors, motor circuits, and controllers. Article 450 covers transformers and transformer volts. Article 500 covers hazardous classified locations. In the described situation, the 30 amp ground fault reading is an abnormal condition that poses a significant safety risk. The immediate action of opening the 2500 amp MCB and observing the drop in current was a correct diagnostic step. The next step should include a thorough visual inspection of the 2500 amp MCB compartment and all associated wiring and connections. Following the visual inspection, perform insulation resistance tests using a megameter. Remember to de-energize and isolate the circuit before performing any insulation resistance tests. Compare the measured insulation resistance values with the manufacturer's specifications. Any readings below the specified minimum indicate a compromised insulation and a potential fault location. Consider using a ground fault locator. These devices can help pinpoint the exact location of the ground fault. They typically work by injecting a signal into the grounding system and then tracing the signal to the fault location. If the visual inspection and insulation resistance tests do not reveal the fault, it may be necessary to perform more advanced troubleshooting techniques, such as time domain reflectometry, or TDR. TDR is a method of locating faults in cables by sending a signal down the cable and then measuring the reflections. The reflections can be used to determine the distance to the fault and the type of fault. Also, perform a thorough check of all connections within the 2500 amp MCB section. Look for any signs of corrosion, looseness, or damage. Tighten any loose connections and clean any corroded connections. If any damaged wires or components are found, they should be replaced immediately. After completing the repairs, thoroughly test the system to ensure that the ground fault has been eliminated. Use a ground fault tester to verify the proper operation of the ground fault protection system. Monitor the system for any recurrence of the ground fault. Regular maintenance and testing of electrical equipment can help to prevent ground faults. This includes visual inspections, insulation resistance tests, and ground fault protection system testing. It is also important to keep electrical equipment clean and dry. Dirt and moisture can contribute to insulation breakdown.